Thank you very much for this invitation. Uh, I will show you joint work with Professor Lev Gordy from Tübingen University. It's a long-term research that we have. Recently, we published a paper that it's a semi-reviewed, but it was published in any way. And it is related to that talk, but I will not speak about this until the end of the talk. Let's deal with this talk as compressing natural deduction proofs in the minimal implicational logic. Okay, so only to remember natural deduction proofs. For example, this is one proof natural deduction. We will deal only with these two rules: imply elimination and imply introduction. Here at the end we have an imply introduction. From A we derive C, so we have A implies C. Okay, that is one other example. That is Wickspear's formula. This formula needs, in order to be proved, it needs two occurrences of this formula discharged here. At least twice this formula has to occur in the proof. If we consider a normal proof, of course. If you don't know what's a normal proof, I will speak about that, not define precisely. We will represent derivations in a simpler way using graphs. For example, this rule here we will present as this piece of graph, and the implication introduction. We have a graph that has a root v, and a rooted graph, and has some occurrences of these formulas here that are nodes. So we can derive A implies B, and we use these red edges to indicate that we have this discharge here of only of the all these edges that were discharged by the rule. There is a way to not using this this representation with this red. That is using dependent sets. For example, here we have the graph that represents this proof here, and using this dependent set that indicates that B depends on A by this edge, B depends on A implies B by this edge, so B depends on the union of these formulas, and so on, until we reach implication introduction. So we have the discharge is represented by removing the discharge formula from the set of discharging of this dependent set. We use a grid introduction rule, so to say. Anytime we apply an introduction implication, we discharge all the occurrences that were to be introduced, all of them. It's a grid way of implying introduction, but we have an easy way, an easy theorem that ensures that this does not disturb the fact that we have all tautologies using this grid introduction. It is an easy. From this point on, You only apply vacuous introduction. Okay, this is the way. So in this way, we can represent this second, this sixth slide. We are, instead of using sets of formulas, we use bit strings. So bit strings that represent the set, the dependent set. And for this, we only have to provide a linear total order that is a totally arbitrary given, but it's part of this way of representing natural deduction. So from now on, these dependent sets are labels of these edges, and we can verify that a graph like that is a valid proof only by inspecting that the label of the edge going out of a node is the sum of the labels of the labels of the edges going in this node. In this case here, we have when we apply imply introduction, and when we apply imply elimination. When we apply imply elimination, this is the sum. When we apply imply introduction, this is the difference. We remove the bit if it is turned on. We put it turned off after the application. So since this is always the same for a proof, we will not represent this anymore. Okay, this is bits. Okay, this is an example of a natural deduction proof. In this, only to say, M implies the minimal logic only with the implication. This is we can simulate polynomially any proof in intuitionistic logic by a result from a statement in 74, I think, 78, 74, that we can provide a cubic length formula from the original formula in intuitionistic logic that is provable if and only if the original one is proven. I will not go into this kind of detail because we are already in minimal logic and minimal implicational logic. So this is a proof. Only to see it, you can see that this proof is a proof of a Fibonacci, a sequence of formulas that resembles Fibonacci growth, and all of those proofs have a property that they are lower bounded by the Fibonacci number of the conclusion, A7. So the size of this proof is a Fibonacci number of 7, but the height of the proof is linearly depend on the 7, or linear depend on the conclusion, on the size of the conclusion also, okay? Well, I have to diminish this. I think I was in this size, okay. Well, how we measure, estimate the size of a proof? No, this is, I've already said that. No? We give a total order, and we have this tree that represents the proof. And of course, we have a polytime algorithm to check if a tree of this kind is a proof or not of the conclusion. Okay, you have to have the label after the conclusion should be 000, the bit string 0, and all the rules have to be correctly applied. So we have a linear algorithm on the size of this proof. Okay, but only to put something in advance, there is a way of expressing the existence or no existence, that is the no existence of Hamiltonian cycle in graphs by means of formulas in this logic, in a way that if there is no Hamiltonian cycle, we have a tautology. The size of this proof is cubic on the size of the graph, number of vertices of the graph. For example, for a graph that I'm not showing it here, but the proof has this appearance. A graph with five nodes. Here is the proof that it is not Hamiltonian. Okay. Again, we have this phenomenon that is the size of the graph is exponential, in fact, but the height of the graph is linear on the size of this cubic size of the formula. I omitted here the introduction steps because it's only a strip of introductions that all the formulas that are top formulas are discharged after here. Q here is the way that we so we conclude Q. Q is the way that we simulate the absurd in this translation from intuitionist logic to is a new letter variable, propositional variable. Okay, so back to the slides. There is this graph here has 5 nodes. The Peters graph, it's a famous graph that has no Hamiltonian cycle, but the size of this graph is much bigger, very big. This was obtained, of course, by a automatic theorem prover, but using a strategy that was handwritten, not automatic, in fact. Well, this is the proof that a graph with 10 nodes is not a Hamiltonian graph. Here again, we have that the height, it's, in fact, this is a theorem. There is for every graph with this property of being non-Hamiltonian, there is a normal proof in this language with implication that has the height of this normal proof is linear on the conclusion, but the size could be, in general, the size is exponential, because this is a naive proof that take all the possibilities of the path to be, and in the case that is no Hamiltonian, all the possibilities go to prove an absurdity. Okay, so but what I'm speaking about huge proofs. Okay. What's a huge proof? An exponential proof is a huge proof. But what's an exponential proof? Let's be more precise on these definitions. The size of a proof, it's not, it has to be related to the size of the conclusion, of course, because anywhere we have only numbers, and numbers can be compared only. There is no relationship between the conclusion and the size of the proof. So we have a we see this relationship between conclusion and the size of proof as a ratio, and the size of proof is the bigger is this ratio, the biggest is the size of the proof. Okay, so and we consider a proof as smaller whenever it is feasible. Feasible using a conjecture proposed by Cook and Karp. It's a synonym for polynomial time, or in the case of reading a proof, polynomial sized proof. Okay, hard or big proofs will have to spend more than polynomial time to be verified. This is a computational complex view of proof trees. So a proof that you have to use more than polynomial time to check that it is a proof. It's a huge proof. So let's define this precisely. Well, there is this fact here. It's a kind of parenthesis, but we will use this afterwards. The proofs in general that we need to inspect or to study this hugeness phenomena doesn't need to be general. We can focus only on linear height proofs, because of there is this result from Hudemeyer that shows that we can prove in sequent calculus every minimal logic tautology in a proof that is linear in the height, and we have translated this to natural deduction. Okay, but there is a thing to say about that. If I forgot, please remember. Well, huge proof is a proof tree is considered huge whenever we won't take a proof as an isolated thing. We have to compare the growth of the proof as inside a family, because in computational complexity we have this linear speed-up theorem that says that computational complexity scales linearly. So we cannot take a proof and disprove it exponential. There is another thing too that is completely related. A finite set of proofs doesn't matter how big they are. If I only have a finite many big, in the sense of huge proofs, they doesn't matter for the computational complexity, because we can put all those things inside the program that verifies all the conclusions, and we have a precompiled program that can check this in constant time. Okay, so this finite set of proofs doesn't matter. So our definition of a huge proof is in terms of a family. We will say that a set of proof trees is super polynomial, because it's huge. Anything that is more than polynomial, it's huge. It's huge in the sense of computational complexity. So a set is a set of super polynomially sized proofs if and only if it is lower bounded by any polynomial. So to say, for every p, that's the degree of the polynomial, we will consider p from 2 on, there is no problem. There is a number that every proof that the conclusion has this size, n bigger than this n0, the size of the proof, here we have the size of the conclusion. Here we have the size of the proof is bigger than the size of the conclusion to the power to this degree, okay? So intuitively, a family of super polynomial proofs has no polynomial upper bound for almost all members. Almost all is a slogan for sorry, is a slogan for this. There is a number that from this number on, everything is super polynomial. So this is what we consider a huge proof. Okay, this definition is quite adequate if we see the fact that for every set of super polynomial proofs, if you set if you consider this function that to every number provide you the size of the minimal proof that has a conclusion of the size n, this fs, it's well defined for this, from this s. If this s is an infinite set in the sizes too. The fact is that if S is a set of super polynomial sized proofs, then this F, sorry, there is a mistake here. This Fs here is this F here. No, this Fs is a super polynomial function, and there is no mistake. F is a E and F is super polynomial if and only if F has every polynomial as a lower bound, okay? So this is what we take as a huge proof. So only to remember or to show that no one has to know that what is a normal proof. Here we have a normal proof is a proof that does not have this kind of figure here. You have an implied introduction followed by an implied elimination. This is what we call the tour or maximum formula, depending on the terminology. And it's easier to not, this formula here is more complex than B and A. And you can see that you don't need this formula because you can transform this derivation here in this derivation here, only putting this A here. Of course, the size can be more, can be bigger, but we are not concerned with that at this moment, okay? So a normal derivation is a proof or a derivation that does not have this kind of the two. So in a normal derivation, we have this, the size of a branch, only to say, I forgot to say something here. A branch is a sequence of a branch here. Here we have a branch. We have an implied elimination. And the branch starts with a top formula and finishes either in the conclusion or in the a minor premise of an implied elimination. So we have this branch here, starting here and ending here. We have this branch here, starting in this A and ending here. We have this branch that ends here and start here, and this branch here. So the branch that finishes at the conclusion is the main branch or principal branch, and the others branch are classified in the hierarchy. So this is the secondary branch, this is a tertiary branch, and so on, okay? we will use this for a result in the sequence. Okay. Well, since since a proof is normal, if we consider a proof that is normal, the branch is has a first part that can be empty, only elimination rules. We have the minimal formula and the introduction rules. We cannot have an introduction rule followed by an elimination rule in the same branch, because this is a detour. Okay, so this ensures that we have this subformula principle for branches. Every formula here, because of the format of the implying elimination and implying introduction, every formula either is subformula of alpha or subformula of delta. This is the top formula, and here we have the conclusion of the branch. Okay, if you combine branches, then we have this subformula principle for the whole proof. So we have a branch that starts with delta 1 and finishes at alpha, and alpha is subformula of alpha implies b. Alpha implies b is subformula delta 2. So both are subformulas either from delta 1 or from delta 2. Beta also is a subformula of delta 2. So we have this subformula property spreading for all the proof. So we will working with normal proofs. For tautology, we don't need these non-normal proofs, because there is this normalization theorem, firstly proved by Gansen. Had some problems with classical absurd, but after solved by Pravitz in 1965, that ensures that for every proof we have a normal proof. So we don't need to worry about no normal proof in proofs, in proving tautologies, or well. What I want to show you is that in every family of super-polynomial and linearly height upper bounded normal proofs in natural deduction, that there is a this stars here has some I will explain in this logic. Every proof that is in this family, almost every proof, less than a finite number, are super-polynomially redundant. What is a proof that is super-polynomial redundant? I will, the function that estimates the number of subproofs in each level that are repeated in each level is also a super-polynomial function. So to say, if you use this abuse of language that is super-polynomial many times, so pi is super-polynomially redundant if and only if there is a subderivation, pi prime, and a level m of pi, such that pi prime occurs super-polynomially many times as subderivations of pi prime. This will be formalized precisely in the following. Okay, the first thing that we have to observe, it's a technical fact that it's important to count in proofs. Let's see this proof here. Okay, we have two minimal formulas here. Q, that's the minimal formula of this branch, and this other Q, that is the minimal formula of this branch here. Okay, so they are the same formula, but they are in different positions in the syntax tree of the conclusion. So instead of count they as the same formula, we will consider that this Q here is attached to this Q in this syntax tree, and this Q is attached to this Q in the syntax tree. So what is the advantage to consider a natural deduction with this linking to the syntax tree of the conclusion for tautologies, okay? Is that we can distinguish between different minimal formulas that determine uniquely which is the top formula to which they belong, to which branch they belong. So if you see that this Q here, it belongs to here, so the minimal formula to which it belongs, it's only to go up by the left edge until reach a formula that you cannot go by the left again. So it's a left ancestor of a node that is not a left child of anything. Okay. In this way, if we count the number of minimal formulas, we have this for each minimal formula, it belongs to at most one branch, one type of branch. No, not one. The instance is of one type of branch. So we have this concept of E-mapped natural deduction normal expanded proof. An expanded proof is a proof that the minimal formulas are all atomic. We can produce expanded proofs, normal expanded proofs from any normal proof. Okay, there is a very easy pattern. I will not show here because of the time, but what is important that we are now taking this kind of representation of normal proofs. It's a E-mapped natural deduction normal expanded proof. So to say, a proof with syntax tree of the conclusion, and this linking here is a function. Okay. The definition is here, and we have this lemma that I said before. For any proof of this kind, the number of different types of E-parts occurring in this proof is at most of the size of the syntax tree. Only to remember, the syntax tree is of the size of the formula. Okay, we have one label for each subformula, and the number of subformulas is linear on the size of alpha here. Okay, so we have a linear number of top formulas, or a linear number of branch too. Okay, types of branch, not instances of branch. So our result is still now stated in a more precise term. We are still considering linear height proofs. Okay, so we have this theorem. For all P is the degree of a polynomial. We will take P bigger than 3. Okay, we will see why this is in this way. For all P pi belongs to this set that is super polynomial, if the size of the proof is bigger than m, that is the size of the conclusion, to P, then we can prove that there is a subderivation pi s of pi and a level mu in pi such that this derivation has at least m to p minus 2 instances occurring in this level. Okay, so to say, a big proof has a lot of a proof that is more than the size of the conclusion power to 10 has at least the size of the conclusion power to 8 subproofs, instances of a same proof. Okay, so it's the size of the proof carries with it the size of the repetitions of the same proof. Okay, in this factor, that's 2. Of course, if this family is super polynomial, the repetition of the function that estimates the repetition of subproofs in the proofs is also a super polynomial function. So this is the theorem, and this is what we will prove. In fact, we prove this by 2 lemmas. The first lemma is only to show that if the height is linear, and we have linearly many subformulas, we have a proof that is bigger than m to some power, then we have at least one level that is repeated m to p minus 1. Okay, this is a combinatorial principle. And there is another combinatorial principle here that if I have a branch that in a super polynomial proof, if I have a branch that repeats m to p, then we will have this is the following. We will have this branch induces the repetition of a subderivation. Okay, this is done by this proof is done by an inductions on the reverse rank of this of the level of the branch. Okay, of this hierarchy of branches. All the details of this are in a paper I will show you, because I cannot provide details here. So, using this theorem, in fact, a corollary of this theorem, that is, in every family of super polynomial proof and linear height, there are proofs that are repeated super polynomially many times. So, in this case, how we will compress a proof. We will use this redundancy that is intrinsic to the big proofs to collapse all the proofs in only one, all the subproofs in only one. Let's do this graphically. Suppose that we have a proof 3, and that is this proof satisfies the condition of the theorem, so it's bigger than m to p. M is the size of the conclusion, is the label of this root here, and it's linearly upper bound on the height. Okay, so we have we have a sub proof that repeats very much. So super polynomially m to p minus 2. Okay, so what we will do, we will collapse all these proofs in only one proof. Okay, all other instances were collapsing this instance here. We use these edges here to take track, to have a kind of memory which is the root that we have to read the proof. So to say, we start at the top formulas, and for each top formula, we have some edges arriving. We store the label of these edges in a register, and we go down until we reach a node that has this bifurcation, trifurcation, so to say. Okay. Then we will check if this the dependence set that arrives here, it's according to, it agrees with the label of this edge here. So that it was introduced during the collapse. So we have this DAG. We are transforming proof tree in a DAG, in a directed acyclic graph. In this way, if I have a m to p minus 1 occurrence of this proof, then we divide the size of the proof by the size of this subproof to m to pi minus 2, sorry. Okay? If this proof is big, so to say, it's more than m to p, then we can apply we must apply the theorem, so to say, the corollary, to this subproof, and we have a recursive method to compress the proof. Okay. In this figure here, we have this rectangle is already compressed, and inside it we have it is a big proof too, and it's more than the degree depth of the whole proof. So we have this repetition, and we can collapse again and adjust this collapse adjusts the edge in a way that the root of the dependent sets are consistent with the original proof roots. Okay, so this compression of huge natural deduction proofs, it's obtained by this way, in a recursive way, and we have at end a polynomial. We have a polynomial time. In fact, it's linear time that is able to read this kind of DAGs and say if it is not if it is or not a proof of the tautology of the conclusion. Okay. The recursive method is here. It's stopped when the proof is not bigger than the size that we want to compress. Okay. In this case, we only return the proof. Okay. In all other cases, we start by compressing bottom up the application of this redundant subgroups. Okay, so by induction on the recursion here, we can prove that the algorithm stops providing a polynomially sized direct acyclic graph that is the certificate of its conclusion. Look that if I give to the recursive method a proof that is superpolynomial includes exponential. Okay, we will end up with a polynomial, so to say, with a degree less than p, proof that is less than the size of the conclusion to p minus 1. In this case is 1, but well. Well, what is the applications of this? The first application is that we can use this recursive method it's a method. It's not easy to do that, okay? Using computational terms, but we can use that to provide a proof, an alternative proof that QNP is equal to NP. It's only we can use this theorem and the compression on all the graphs, on all the proofs that are that prove that a graph is non-Hamiltonian. We will produce a polynomial size verifiable in polynomial time certificate that a graph is non-Hamiltonian. So to say, we are proving that co-NP is included in NP. If you prove that, you can prove easily that they are equal. Okay? In this, this is the strategy. Anyway, if you can find any mistake or you cannot, you are not convinced, we implemented. There is another application that we implemented this compression process and applied in some big, huge proofs that we generate, and they are proof on the size of graphs, and compare with Huffman code. If you see these blue bullets, dots are the, this in Portuguese here, the size of the file. So we are comparing the size the size of a proof as the number of symbols in it, okay? Compared with Huffman code, that is a string compression algorithm. So Huffman code is almost linear, the compression, while our compression is exponential, okay? Last. Here we have the ratio, the compression ratio, okay? And here we have the size of the formula. Here is the our algorithm of compression. It's here is 95% the ratio. In Huffman, that is a benchmark, is an old benchmark, but it's a benchmark for compressing strings. So if in any way we have a compression, an efficient way of compression proof. If you remember here, we have here a big proof, and we have it's compressed. The nodes here are fewer than the nodes in the original, and all those edges are quadratic in the size of the nodes. But the figure has the string are, as we have seen, the strings are much smaller. So the main references is we have this proof compression and P versus P space. We have only to, well, we just published a proof that in P is equal to P space that I didn't, I will not present, it's unable to present in 1 hour or less. But the proof that I show to you is here, okay? If you send me because it's not, I submitted to archive, but it's not uploaded yet. I can send you by email if you send me an email. Okay, thank you.